I'm presenting a problem about canonical correlation analysis, CCA, a statistical method to find the best linear relationships between two datasets. We'll use Sklearn's CCA function to analyze gene expression and clinical data. I'll then quiz you on the meaning of the output, specifically focusing on the weights applied to each dataset. Statement A says that x_weights_, shows the weights used to combine the gene expression features. Think of these weights as multipliers for each gene. This statement will be crucial when we explore the calculation of canonical variates for X. Statement B claims that y_weights_, gives us the correlation between the original clinical measurements and the new clinical variates that CCA creates. I'll show you why that is incorrect. Remember, y_weights_, represents the weights, not the correlations. Statement C is about the size of x_weights_, and y_weights_. It suggests that the number of columns equals the number of samples. But in fact, the number of columns represents the number of features, not the samples. I'll demonstrate this when I explain the true meaning of this attribute. Statement D proposes that we can obtain the canonical variates, the new combined features, for dataset X by taking the dot product of x_weights_, and the transpose of X. That's a key calculation in understanding CCA, and I'll show you how this statement will be important. I want to make sure you're comfortable with CCA, canonical variates, the new combined variables, and the meaning of x_weights_, and y_weights_, the coefficients that create these combined variables. These are essential to solving the problem. We'll need to understand the Sklearn CCA function and its attributes. No complex math is needed, just conceptual understanding. I see dataset X represents the gene expression levels. This is one of the two datasets used in the canonical correlation analysis, CCA. We're looking at how gene expression relates to clinical measurements. This is the specific model we use, from the Sklearn library in Python. It performs CCA, a statistical method to find the relationship between two datasets. Pretty cool, right? This attribute holds the weights applied to each gene expression feature, from dataset X, to get the canonical variates. It shows how much each gene contributes to the combined effect. Think of it as a recipe. Each weight is the amount of an ingredient. Similar to x_weights_, but for dataset Y, clinical measurements. These are weights that determine how much each clinical measurement contributes to the final canonical variates. It's like a different recipe, with the weights as ingredient amounts. These are the new variables, calculated by combining the gene expression levels, dataset X, using the weights from x_weights_. They're linear combinations that maximize correlation with the corresponding variables from dataset Y. It's like making a new dish using the x_weights_ recipe. These are analogous to the canonical variates for X, but derived from dataset Y, clinical measurements, and the weights in y_weights_. They represent the best linear combination of clinical measurements to correlate with gene expression. It's like making a different dish, Y, with the y_weights_ recipe. I'm asking you to assess the truthfulness of 4 statements about the output of canonical correlation analysis, CCA, using the Sklearn library. Specifically, we're examining x_weights_, and y_weights_, which hold the weights used to create the canonical variates. This is a core concept in CCA, focusing on understanding how these weights relate to the original data and the resulting canonical variates. This statement is absolutely correct. The x_weights_, attribute directly gives you the weights applied to the features of your X dataset to compute the canonical variates for X. These are the coefficients in the linear combination that defines each canonical variate. This is incorrect. y_weights_ provides the weights used to create the canonical variates for Y, just like x_weights_ does for X. It does not directly represent the correlations between the original Y features and the Y canonical variates. Nope, this is wrong. The number of columns in x underscore weights underscore equals the number of features in dataset X, and the number of columns in y underscore weights underscore equals the number of features in dataset Y. It's features, not samples. I agree with this statement. You're right. The canonical variates for X are calculated by multiplying x underscore weights underscore with the transpose of the X dataset. This is a matrix multiplication operation. The result will be a matrix where each column represents a canonical variate. I'm analyzing gene expression data, X, and clinical measurements, Y, using a statistical method called canonical correlation analysis, or CCA for short. CCA helps me find the best linear combinations of these two datasets that show the strongest correlation with each other. Think of it as finding the hidden connections between genes and patient characteristics. This is the main question. I'm going to evaluate the accuracy of statements about the weights that the CCA model produces. This statement is correct. The x underscore weights underscore are the numbers I multiply each gene expression feature with to get the canonical variates for X, which are the linear combinations that maximize the correlation. Think of them as the recipe for making the best combination of gene expressions. This statement is incorrect. The y underscore weights underscore are the weights, not the correlations. They're the multipliers, like the x underscore weights underscore for the Y data. This is wrong. The number of columns in x underscore weights underscore and y underscore weights underscore matches the number of features, genes or clinical measurements, not the number of samples, patients. This is absolutely correct. I take the x underscore weights underscore multiply them element-wise by the transposed gene expression data, X, and the result is the canonical variates for X. It's like applying the recipe. I'll explain what each attribute means in the context of canonical correlation analysis, CCA. We're using scikit-learn's CCA here, a technique to find the best linear relationships between two datasets. Think of it like finding the most aligned directions within two different spaces. This question tests your understanding of these attributes after you've used the CCA model. Are you ready? This statement is incorrect. y underscore weights underscore gives you the weights, or coefficients, that are applied to the original features of dataset Y to create the canonical variates for Y. It doesn't directly give the correlation. Think of it like this. The weights show you how much each original feature contributes to the new, combined feature, the canonical variate, not its correlation with the new feature. This statement is correct. The canonical variates are the new variables that CCA creates. They are linear combinations of the original features. To get the canonical variates for X, you take the weights, x underscore weights underscore multiply them by each feature in X. This is the dot product. And that's how you get the new values for the canonical variates. It's like making a recipe. The x underscore weights underscore are the ingredient amounts. X are the ingredients. And the canonical variates are the final dish. This statement is absolutely correct. Spot on. The x underscore weights underscore are the coefficients used to create the canonical variates for dataset X. It shows how much each original X feature contributes to the new, optimized feature, the canonical variate. You can think of these weights as the recipe for making the new canonical variates from the original features in X. Nope, this is wrong. The number of columns in x underscore weights underscore and y underscore weights underscore is equal to the number of asterisk features in X and Y, respectively, not the number of samples. Each column represents a weight for each feature used to create the corresponding canonical variate. The number of samples is a different dimension altogether. Think of each column as a coefficient related to a specific feature. We have as many columns as we have individual features in the datasets. I'm asking you to determine which statements accurately describe the meaning and use of x underscore weights underscore and y underscore weights underscore which are outputs from a canonical correlation analysis, CCA, using scikit-learn. CCA finds the best linear combinations of two datasets, here, gene expression and clinical measurements, that maximize their correlation. These weights are crucial for interpreting the results. This statement is correct. X_weights_backquote provides the coefficients or weights that are multiplied with the features of the gene expression dataset, X, to compute the canonical variates for X. Think of it like this. Each feature in X gets a score from X_weights_backquote, and these are combined to give a new score representing the canonical variate. This is incorrect. Y_weights_backquote gives the weights applied to features in Y, clinical measurements. To calculate canonical variates for Y, it does not directly represent the correlation between original Y features and canonical variates. Although there is a relationship, the weights are not the correlations themselves. This is incorrect. The number of columns in X_weights_backquote corresponds to the number of features in dataset X, and similarly, the number of columns in Y_weights_backquote corresponds to the number of features in dataset Y. The number of asterisk rows would relate to the number of canonical components. This is correct. You absolutely can obtain the canonical variates for X by performing a dot product of X_weights_backquote and the transpose of dataset X. This is the core of how the canonical variates are computed from the original data and their weights. I'm looking at the weights from a canonical correlation analysis, CCA, model. These weights, X_weights_ and Y_weights_ are super important because they tell us how much each original feature contributes to the new, combined features, canonical variates, that CCA creates. We'll look at whether each statement correctly describes them. Let's dive in. This statement is absolutely correct. X_weights_ gives you the recipe for making the canonical variates for the X dataset, e.g., gene expression data. Each number in X_weights_ tells you how much of each original gene expression feature to include in that canonical variate. It's like a mixing bowl for data. Nope, this one's wrong. Y_weights_ doesn't represent correlations. It gives the weights, just like X_weights_ but for the Y dataset, e.g., clinical measurements. Each number tells you how much to scale each original clinical measurement feature to get the canonical variate. Think of it as a different mixing bowl, this time for the clinical data. This is incorrect. The number of columns in X_weights_ and Y_weights_ match the number of asterisk features asterisk, not samples, in X and Y, respectively. The number of rows would be the number of canonical components computed. Totally right. This is how you actually calculate the canonical variates for X. You take the weights, X_weights_, and multiply them by the original data, X, which is transposed to get the correct dimensions. This gives you the new, combined features. It's like applying the recipe from X_weights_ to the ingredients in X to make the final dish. It's all about combining ingredients correctly. This refers to the matrix of weights applied to the features in dataset X to obtain the canonical variates for X in CCA. These are the coefficients that determine how much influence each original feature has in the formation of the new canonical variates. I think of it as a set of levers, each controlling the contribution of a gene expression feature to create the canonical variates. Similar to X_weights_, this term refers to the matrix of weights used to form the canonical variates for the Y dataset, clinical measurements. Each value in Y_weights_ indicates the contribution of each clinical feature to its corresponding canonical variate. These are the levers to control the clinical features in the CCA process.